Hi, in this lesson we will see about dynamic programming. Dynamic programming is one of the important key topics when you are preparing for the interview. Dynamic programming might be challenging at first. Once you practice good amount of problems in the dynamic programming, you will find it really easy. I will keep on posting videos regularly on dynamic programming in different complexity levels, so make sure you subscribe to this channel. To understand dynamic programming better, I personally recommend to have some understanding in recursion before proceeding with dynamic programming. Refer to my video tutorial on recursion, the link of which I gave in the description. Dynamic programming is an optimization strategy for a recursive solution. This reduces the time complexity from exponential to polynomial. We will see this in depth while analyzing how dynamic programming improves the recursive solution time complexity. When we need to use this dynamic programming? This is very important key question. So we have two properties. If your problem satisfies any of these property, then dynamic programming is good candidate to solve that problem. We will see those properties. First property is when you find a problem which can be split into overlapping subproblems. So what is overlapping subproblems? For example, find the fifth element in the Fibonacci series. Fibonacci series at an index is found by adding values present in index -1 and index -2, that is, adding the preceding two values. The series starts with the elements 0 and 1. It goes like 0, 1, 1, 2, 3, 5 and so on. Here the Fibonacci series starts with 0 and 1. The third element is calculated by adding the value 0 and 1. So the third element is 1. The fourth element is found by adding the values present in the index 2 and 3. So the fourth element is 1 plus 1, which is 2. The solution can be achieved by adding the element at the index 3 and index 4. To get the index 3 value, add index 1 and index 2 value. This is one subproblem. Index 4 value can be found by adding the values at index 2 and index 3. This is another subproblem. Here if you notice, these subproblems overlap. If you find overlapping subproblems in your problem, then you can use dynamic programming. The next property is when you find a problem which is said to have optimal substructure. That is, if an optimal solution can be constructed from optimal solutions of its subproblems, then it is said to have optimal substructure. We will see this with the Dijkstra's algorithm. We are not going in depth in Dijkstra's algorithm. I will just give a gist about Dijkstra's algorithm so that you will understand optimal substructure better. In Dijkstra's algorithm, if you want to find the optimal path from node 1 to node 4, we will find the optimal solution from node 1 to node 2, then from node 1 to node 3, then from node 1 to node 4. Here, the problem is divided into optimal substructure. That is, we are finding the optimal path between 1 to 2 and 1 to 3 and 1 to 4. In each subproblems, we are finding the optimum solution and we are arriving at the final result. This is called as optimal substructure. So if you find optimal substructure in your problem, then you can use dynamic programming. Now we know when to use dynamic programming. We will see how to optimize the recursive solutions with dynamic programming. There are two ways to do it. They are memoization or top-down approach, and the second one is tabulation or bottom-up approach. We will see memoization or top-down approach first. We will see this in depth using the Fibonacci series example. For this dynamic programming class, I use this Fibonacci series example. We will write a simple function which finds the element at the nth index position of the Fibonacci series using recursion. Whenever we are handling the recursion, we need to understand the base case. The base case is the condition in which the recursive loop terminates. In this problem, the base case is if the n is less than or equal to 1, return n. That means for the index position 0, the value is 0, and for the index position 1, the value is 1. To find the element at the index position n, we need to add two preceding elements. That is, return Fibonacci n-1 plus Fibonacci n-2. Here, we are recursively calling the Fibonacci function again with the value n-1 plus Fibonacci n-2. We will just return Fibonacci n-1 plus Fibonacci n-2 here. Here this code finds the nth element in the Fibonacci series recursively. The time complexity of this solution is exponential and the space complexity is order of n if you consider the space occupied by the stack in recursive solution. We will see this recursive solution in depth with the tree structure explanation. I want you to understand this tree structure better because that is the building block of memoization and dynamic programming. So here we want to find the value of the element at the fifth index position. So we are calling this Fibonacci function with the input 5. Fibonacci function calls itself with the input value 3 and this calls itself again with the input value 2, which in turn calls itself again with the input value 1. So when it reaches 1, it reaches the base case. So Fibonacci of 1 is 1. We know that subproblem result. Then it moves to the right side, which is 2 minus 2. This returns 0 because this also comes under the base case. So it returns 0. For the value 3, the right hand expression is Fibonacci 1. We reach the base case here again. So Fibonacci of 1 gives us 1. For the value 4, the right hand expression is Fibonacci 2. It divides into 2. Fibonacci 1, which gives us 1 because this makes the base case, and right hand expression is Fibonacci of 0, which gives us 0. Here we got the value at the index position 4, which is 2 plus 1 gives us 3. So the Fibonacci of 4 is 3. The right hand expression for this input value 5 is Fibonacci 3, and this calls itself again with the input value 2. It calls itself again with the input value 1, which makes the base case and returns 1. And the right hand expression for this input value 2 is Fibonacci 0, which returns 0. So the fib of 2 is 1 and fib of 3 is 1 plus 1, which is 2. So the final answer is fib of 4, which is 3, and fib of 3, which is 2. So the output is 3 plus 2, 5. Now we have drawn this tree structure. Now start analyzing this tree structure and you can be able to see the same subproblems are repeating again. Here we are repeating the same subproblems and computing it again. For example, fib of 3 is computed twice and fib of 2 is computed thrice. This is where the memoization approach comes into the picture. That is, whenever we are coming up with subproblems, we need to store the results of the subproblems, and if you see the same subproblem again, then we can use the subproblem result which we have computed already directly rather than computing it again from the scratch. This is the main motive behind memoization. So we will see how this tree changes after we store the subproblem results. So here we need to find the value of the element present at the index position 5 in the Fibonacci series. So we are calling the fib function with the value 5. So this fib5 calls itself again with the value 4. This again calls itself with the value 3. This again calls itself with the value 2. And this again calls itself with the value 1. Here fib of 1, it reaches the base case. So fib of 1 is 1. We know that subproblem result. And the right hand expression for the value 2 is fib of 0. Fib of 0 gives us 0. So the fib of 2 is 1 plus 0, which is 1. Now we have computed the result for this subproblem, fib of 2. So store its value 1, and right hand expression of 3 is fib of 1, which is 1. So fib of 3 is 1 plus 1, which gives us the result 2. Now we have computed the result for this subproblem, fib of 3. So store its value 1. So for the value 3, the right hand expression is fib of 2. We have already stored the value for fib of 2, which is 1. So we are directly using that value which we have stored rather than computing it again. Fib of 4 gives us 2 plus 1, which is 3. Store this subproblem result. The right hand expression for 5 is fib of 3. We already stored the value for fib of 3, which is 2. So 3 plus 2 gives us the value 5. This is how the tree looks after we have applied the memoization. So this is memoization. Memoization is storing the subproblem's value and using it when we see the same subproblem again. This reduces the time complexity and this also reduces the redundant computation. The memoization is also known as top-down approach because we are starting from the root node and going till the leaf node. We will see the Java implementation of this memoization. So here we are using additional array which holds the subproblem results. So the fib function takes two parameters. One, the n, which is the index value which we need to find, and an array f to store the subproblem results. So here the base case is if n less than or equal to 1, then return n. We check if we have already computed the subproblem result. That means If computed, we will return the value. If not, then compute the subproblem result and store it in an array. And return the subproblem result for the initial index value n. And this is the Java implementation of memoization which we have applied on top of recursion. This is top-down approach. The time complexity of the above solution is order of n. We have reduced the time complexity from exponential to order of n. And the space complexity is order of n for the array which stores the subproblem results. Next, we will see about tabulation or bottom-up approach. Tabulation means instead of using the recursive approach, start from the subproblem results we already know and build the subproblems on top of it and store these subproblem results iteratively. We will compute the Fibonacci number at the 5th index position using this approach. First, start with the subproblem result we are aware of. We know the subproblem results for the element at the index position 0 and the element at the index position 1. So add these two values, we will get the value at the index position 2, which is 1. Now we will add the value at the index position 1 and 2. We will get the value at the index position 3, which is 2. Now we will add the value at the index position 2 and 3. We will get the value at the index position 4, which is 3. Now we will add the value at the index position 3 and 4. We will get the value at the index position 5, which is 5. Now we have found the value of the element at the index position 5, which is 5. In this approach, we have started with the subproblem results we already know and iteratively solved the preceding subproblems. Thus, we reached our solution. This is tabulation method or bottom-up approach. This is bottom-up approach because we are starting up from the bottom, those values which we have known, and we are building subproblems on top of it, and we are finally arriving at our solution. This is bottom-up approach. We will see the Java implementation of this bottom-up approach. Here, the fib function takes the n, which is the index of the element which we need to find. Here we are initializing array which holds n plus 1 because we need to store f of 0. F of 0 is 0, f of 1 is 1. So we start from the index position 2 and we will iterate it till the n. And to compute for the index position I, we need to add the value at the index I minus 1 and the value at the index position I minus 2. Once this for loop completes, we will get the value f of n. The time complexity of the solution is order of n and the space complexity is order of n because we are using extra array. If we analyze the solution, we need to store only the previous two value, not the entire list. So instead of storing the result in array of size n, we can have two variables which is constant space which stores the preceding two values alone. So this fib function takes n and we are declaring f1 equal to 0 and f2 equal to 0. This to acts as the index position 0 and index position 1 at the first iteration, and during each and every iteration this will keep on change. If n is 0 or 1, return n, and we are starting the iteration from I equal to 2 and we are doing it till the index position n, and we are adding this f1 plus f2 and storing it in temp2, and we are storing the f2 in f1 and temp2 f2. So during each and every iteration, the f1 will be replaced with f2 and f2 will be replaced with the new temp value, which is the summation of f1 plus f2. After this complete iteration, we will return the f2 value, which is the value present at the index n. So the time complexity of the solution is order of n and the space complexity of the solution is order of 1. So dynamic programming plays a key role in your coding interview questions. So whenever you see a problem, you need to analyze whether it follows any one of the two property. One is overlapping subproblem or optimal substructure. If it follows any one of the property, then you can apply dynamic programming. Dynamic programming is easy to understand but very difficult to master it. So subscribe to this channel in which I will keep on posting videos on dynamic programming on different complexity level. Thanks for watching this video. If you find this video helpful, share it with your friends.